Another one more unit is the thermodynamics. Right? So in thermodynamics, in CSIR point of view or other examinations point of view, the basics was not mentioned. That means the questions which can in the CSIR examination point of view not came from the basics, not asked for the basics. Some standards will be maintained. See, listen, before discussing the syllabus point of view, one or two points regarding the thermodynamics. What is thermodynamics? Generally, we may mention that. So the branch of chemistry, it is also a branch of chemistry which deals with the conversion of heat or energy, or heat energy to the mechanical energy, and vice versa. That means again mechanical energy is converted to the heat energy. That means reverse takes place, reverse manner also. That means by absorbing the heat or by emitting the heat, some mechanical work it maybe takes place. Right? And reverse manner also it maybe takes place. That means the thermodynamics case, heat, by absorbing the heat, any chemical and physical changes takes place. By absorbing the heat, the physical and chemical changes takes place. Physical or chemical changes which takes place, that is considered as the thermodynamics, by the absorption of the heat or conversion of heat or energy to the heat energy to the mechanical energy and vice versa takes place. Now, in the thermodynamics point of view, so some terminology we are using frequently. Which one terminology we are using frequently? System. I am not going to be detailed discussion, but just little bit discussion will be given. Right? System is what? System, surroundings we are using frequently in this point of view. System, surroundings, and closed system, and open system, and isolated system, and state functions and path functions. We are using these terminology, and extensive properties and intensive properties. These basics we are using every time. The terminology we are using, that's what I mentioned. What is system? Right? Just now, little bit information will be given. So the specific part of the universe, if which is under our observation. The specific part of the universe which is under observation, which is called as the system. So this particular part which is under our observation, which is called as the system. The rest of the remaining part, whatever the remaining part which is not under our observation, or rest of the system or remaining part of the system which is called as the surroundings. So system is there, another one it may be the surroundings. What is surroundings? So the rest of the system or remaining part of the system, and the surroundings which is capable of conversion of which is capable in a position to conversion of the energy with the system. Surroundings which is capable in a position to conversion of the energy and some other matter or whatever it may be, transfer takes place to the system. That is considered as the surroundings also. That means the rest of the part or remaining part of the system is like this. These are under observation. The remaining part or rest of the part which is incapable of transfer to the system, whatever it may be, the energy, mass or heat or temperature or pressure, whatever it may be, conversion takes place to the system. The remaining part which is considered as the surroundings. System is under our observation, rest of the part is surroundings. Suppose we can take water in beaker. The contents which is mentioned in the beaker, water, like that is under our observation, that is the system. Remaining part is surroundings, like that. System and surroundings is under observation, remaining part. And system and surroundings, right? Surroundings and system can be separated. System and surroundings can be separated. System and surroundings can be separated by a boundary. by a boundary. System and surroundings can be separated by a boundary. That boundary, it may be an imaginary or real. It may be imaginary or it may be real boundary. We may imagine like that, a real boundary. System and surroundings will be separated by a boundary that is imaginary or real. Imaginary or it may be real. The system is in system, it may be one phase are there or many phases also there in system, right? So imaginary or real, the boundary that is separated between the system and surroundings, the part it may be considered as the boundary part, it may be an imaginary or real. So based on the boundary or separation between the system and surroundings, based on the boundary or separated boundary between the system and surroundings, again the systems will be classified based on the boundary. Based on the boundary or separated boundary between the system and surroundings, based on that systems, again it may be classified as closed system. Another one, it may be the open system. Another one, it may be the isolated system. Closed system, open system and isolated system. These systems which are there based on the boundary between the system and surroundings. So what is the closed system and what is open system, like that? First we can take open system. Open system is open. Open system is open. Like that, you can take in a beaker, right? You can take in a beaker. You can, here it is water, it may be there, water and water vapor if it is there. Water and water vapor system you can take, suppose, right? By heating takes place, while heating takes place, here it is, heat can exchange with the surroundings, that means energy can exchange with the surroundings, and some matter also can be escaping takes place, that means mass or matter also can be escaping takes place, that means mass or matter also exchange with the surroundings in a open system, not in closed. It is taken in open, right? So if it is an open beaker, if it is taken, so the water and water vapor, if it is in like that system, it may be there. So water system, it is taken exchanging with the heat as well as the surroundings. In open system is what? The system is open, which can exchange, the system which can exchange, which one? Mass or matter. Mass or matter. And another one, which one? Energy or heat. Energy or heat. So the system can exchange mass or matter, and another one is which one? Here energy and heat. Which one? So this is exchanging takes place for which one? So to the surroundings. To the surroundings. So system can exchange heat and matter with the surroundings. So this is considered as the open system. So exchange mass or matter and energy or heat with which one? Surroundings. With surroundings. In a open beaker, water you can take, that is an example like that. It can exchange with the heat as well as the mass. Now closed system is what? In case of closed system, in closed system, if it is a sealed one, like copper, steel, right, by conducting material like that, so water it may be taken, or water vapor system it is there, water and vapor system is also if it is there. If it is heating takes place like that, if matter cannot exchange with, if it is sealed, the matter cannot exchange with the surroundings, matter or mass cannot exchange with the surroundings, not exchange with the surroundings. So it may be not exchange with the, not escaping takes place, it is closed, right? So not exchange with the surroundings, but due to the conducting material like copper which is taken, right? So this one, heat can exchange with the surroundings. Heat or energy can exchange with the surroundings. Heat or energy can exchange with the surroundings. So mass is not exchanged with the surroundings. Heat or energy can exchange with the surroundings. Heat, it may be transfer takes place from one temperature to another temperature. Different temperature it may be takes place from the surroundings to the system. Heat can exchange takes place. Although it is closed but is not insulated, right? It may be exchanging takes place. Just closed system. Closed system is what? Mass cannot exchange with the surroundings, but energy or heat can exchange with the surroundings. In open system, mass cannot exchange with the surroundings, as well as the energy also cannot mass can exchange with the surroundings, as well as the energy also can exchange with the surroundings. Now what is an isolated system? What is an isolated system? In isolated system, so you can take the system, this system is sealed, fully sealed, that means insulated. By using the insulated material, the system is insulated. Insulated, fully sealed with insulated materials. That means here it is, cannot exchange with the surroundings. That means whatever that heat or energy and matter not exchange with the surroundings. Whatever that it may be there within the system only. That means if it is an isolated system, water vapor system, suppose you can take water and vapor system. Water is converting to the vapor while heating takes place. So the vapor cannot exchange with the surroundings. That means here it is, mass cannot exchange with the surroundings. Mass or matter cannot exchange with the surroundings. Mass or matter cannot exchange with the surroundings. As well as energy also, energy or heat cannot exchange with the surroundings. Heat, energy cannot exchange with the surroundings. That means not leave to the system. Not leaving to the system because highly insulated. This system is highly insulated with the insulating materials. The energy or heat as well as matter or mass cannot escape with the surroundings. Neither mass or matter nor energy. Neither mass nor energy exchange with the surroundings. That means it is not possible, right? So mass and energy or heat neither matter nor energy exchange with the surroundings. That means the mass cannot exchange, energy cannot exchange with the surroundings. This is the isolated system. In closed system, we are using frequently. Closed system is matter is heat or energy is escaping. That means energy can transfer with the surroundings. Mass is not transferred. That means matter is not changed. Matter is not changed. That means number of it may be depends upon the number of moles like that, mass and matter. Later I can explain. In open system case, in open system, mass can exchange with the surroundings as well as the energy can exchange with the surroundings. Next, in an isolated system, mass or matter cannot exchange as well as the energy cannot exchange. That means neither mass nor exchange, neither matter nor energy. Neither matter nor energy exchange with the surroundings. That means mass cannot exchange or matter cannot exchange. Another one is energy cannot exchange or heat. So this is the closed and open and isolated system, right? So all isolated systems are closed. All isolated systems are closed. But all closed systems are not isolated. All closed systems are not isolated, right? So these are very basic points, right? So in CSIR point of view, these basic points are not useful. Basic concepts also not useful. But based on the basics, we can develop the topic. So that's what basics also you learn that first. Right? In your undergraduate level, basics are there. First you read that undergraduate level basics, then it may be the thermodynamics will be very easy to know that, right? Because all basics here discussion is not possible, but based on the basics the topic will be developed. Whenever it is basics will come, I can explain. not a particular position. If particular concept, this basic is required, I can explain that case only, right? But before that, the terminology we can see that. Another one is extensive property. Extensive property. Extensive property and intensive property, both two properties are there. Extensive property and intensive property. What is an extensive property? The property, so this property depends upon, which one? Mass or matter, or size of the particle, mass or matter or size of the particle or amount of the substance which is present in the system. Size of the particle, nothing but the how much amount of the substance which is present in the system. The property which depends upon the mass or matter or amount or size of the substance or amount of the substance, how much amount if it is there. This depends upon the mass or matter or amount of the substance which is present in the system. It depends upon the mass or matter, nothing but the extensive properties. It depends upon the matter, right? So which one is considered as an extensive properties? Mass is an extensive property, and volume is an extensive property, and number of moles is also extensive property. Number of moles, as well as the force, which is depends upon the mass, and area also is depends upon the mass or matter, as well as the all thermodynamic properties. That means Gibbs free energy. G is Gibbs free energy. Gibbs free energy. H is enthalpy. H is what? Enthalpy. G is what? Gibbs free energy. Gibbs free energy. A is what? Helmholtz free energy. And E or U, this is energy or internal energy, like this. Energy or internal energy is E or U, right? The S is the entropy. So all these are thermodynamic properties. These thermodynamic properties are the extensive properties. These thermodynamic properties are extensive properties, right? So these properties will be considered as an extensive properties. And what is an intensive property? What is an intensive property? Another one basic one is intensive property. So the extensive properties, all these properties which depends upon which one? Mass or matter, which depends upon the mass or matter or amount of this substance, all it may be. So general thermodynamic functions, it may be an extensive properties. Now intensive property is what? What is the intensive property? So it's an opposite to that extensive property. That means the properties of the system or properties of the particles which not depends upon or does not depends upon which one? Mass or matter or amount of the substance, mass or matter or amount of the substance which is present in the system. So these properties, that means the property of a system or properties, what are the properties? Are the properties, some properties which does not depends upon the mass or matter or amount of the substance which is present in the system, that is considered as the intensive property. Intensive properties not depends upon the matter. Extensive properties depends upon the matter, right? So which one is an example? Melting point temperature at that melting point, and boiling point, melting point as well as the boiling point, and specific heat which is not depends upon the matter, refractive index which is also not depends upon the matter, or viscosity which is not depends upon the matter, or surface tension not depends upon the matter, entire matter, as well as concentration and density and pressure and temperature. C is the concentration, D is the density, P is pressure and temperature. So these values also not depends upon the mass or matter. Not depends upon the mass or matter. That is considered as the not depends upon the mass or matter or amount of the substance present in the system is called as an intensive property. Now another one here it is there. The two extensive properties ratio or the ratio of two extensive properties, is an intensive property, Suppose in some of the case C is equal to N by V, concentration C is equal number of moles by the occupying value, N by V. N is the which one? Number of moles is extensive property. V is also an extensive property. The ratio of these two extensive properties which is called as an which one? Intensive property. And similar one, density D is equal to mass by volume. This mass is what? Extensive property, mass or matter, and volume is also an extensive property. This is also an extensive property. The ratio of these two extensive properties, which one? Density is an intensive property. Like that, pressure is also. Pressure P is equal to what? Force by the area. How much force can applied in a particular area is considered as the pressure. This is also extensive property. This is also an extensive property. These two extensive property ratio which is called as an the intensive property. And in electrode potential is also pH, and electrode potential is also an intensive properties, right? In addition to this one is also considered as an intensive properties, right? So extensive properties as well as intensive properties, which depends upon the mass or matter, which depends upon the mass or matter. Here in this case, intensive properties are not depends upon the matter or amount of the substance, right? So this is one is extensive, another one is intensive properties. We are using frequently extensive properties because the thermodynamic properties are there, G, H, A, S, E, right? V, all it may be in thermodynamic properties. We are using frequently these functions, right? This function. And work and heat also it may be an intensive properties. Work and as well as heat also. So it may here it is intensive properties, I mentioned that, and extensive properties I mentioned that. So mass, volume, like that it may be mentioned. And another one it may be state function is what and path function is what. Which one? State function and path function. In state function, what is a state function? So in state function, the system or the property of a property is a property which is there, or a function, property or a function, state function. So this function, what are the function which is taken? This function which is depends upon the initial and final stage. Which one is the initial state and which one is the final state? It depends upon only on the initial and final states of the system, the property which depends upon initial and final states. What is the final state and what is the initial state? Not depends upon the path, which one path it may be going takes place, or here in the shortcut form, or it may be long methods it may takes place. That is not a matter. Which one? The function which is depends upon the initial and final states only, that is called as the state function. So all functions like Helmholtz free energy, enthalpy and Gibbs free energy, Helmholtz free energy, and entropy and volume and pressure, all it may be energy, right? All it may be, and which one? State functions. In all thermodynamic properties are, most of the case it may be an state functions. And path function which is there. Path function. Which one is the path function? So the function which is depends upon, which is depends on only, which is depends upon only, which one? Path. Which path it may be going takes place? A to B system is takes place, or A to C, C to B if it is system takes place, or A to D and D to C, or C to B if it is system is takes place. So it depends upon the path, A to D and D to D, C and C to B, like that. Which one path it may be going takes place? That means the system which is depends upon the path, particularly path, that is considered as the path function, is depends upon initial and final states, that is called as the state function. So in path function example, it may be an work and heat. Work and heat, it may be considered as the work and heat, it may be considered as the path functions. Path functions, right? So the energy exchange of the energy takes place within a different temperature which is there, that is considered as the heat. And here it is also exchange of energy takes place in a different, by application of the different pressures, different pressure ranges, the exchange of energy takes place, that is considered as the work, and this is considered as the heat. Heat, it may be in due to the different temperatures, energy exchanging takes place. Due to the different pressures, energy can exchange takes place, work and heat, like that. Now another one is the thermodynamics of the first law. Thermodynamics first law, second law. After that first law and second law, zeroth law will be proposed. Here it is starts with the CSIR point of view. That means it is also basics. First law, second law, zeroth law is also basics, but we are using frequently in further point of view, right? So that's what I mentioned here in this position. First law. Next one is the in continuation form. Which one? First law of thermodynamics. First law of thermodynamics. What is the first law of thermodynamics? Right? So in the first law of thermodynamics, so different forms, different scientists will be given different statements also. Right? So one statement will be given, the energy or heat or energy, according to the first law, the energy can transfer from one form to the another form, one form to the another form. Energy can transfer from one form to the another form. It can change from one form to the another form, but it is impossible to create or destroy it. Create or destroy it. Impossible to create or impossible to create or destroy it. But although it may be changed from one form to another form. Energy is conversion of energy, or energy can transfer from one form to another form. Energy or conversion takes place from one form to another form. It is impossible to create or destroy it. Already it is there, it may be transfer takes place. That it may be statement, one form of the statement. Next, another form. In one form, some amount of energy or heat, some amount of energy disappears, some amount of energy disappears, or some quantity of energy it may be disappears. Same amount will be appears. How much quantity it may be takes place? Equal quantity will appears in another form. Appear in another form. So one form it may be disappears, another form it may be generated. Another one form it may be then generated. Same quantity, how much it may be disappear takes place, same quantity will be appears in another one form. That is also another one statement which is given. And another one statement, so many of the statements also there. If it is an isolated system, the energy of an isolated system is constant. The energy of an isolated system is constant. If it is an isolated system, the energy is always constant. Energy of an isolated system is constant according to statement. Although it may be changed from one form to another form. Although it may be changed from one form to another form. It may be changed from one form to another form, but total will be how much? Constant. Total will be constant. That means system it is losing, surroundings will gain. Surroundings will losing, system will gain. Right? Total energy of the system and surroundings will be constant. Right? In universe, system plus surroundings. What is the universe means? Universe is what? Sum of the system plus surroundings. Sum of the systems and surroundings, which is called as the universe. Right? So system to surroundings, surroundings to system. Like that, or it may be in an isolated system if it is there. If it is particularly in an isolated system, the energy is constant, although it may be changed from one form to another form. One form to another form, total will be constant, which is another one form of the first law of the thermodynamics. Or some amount of energy can be utilized. Suppose it disappears, same quantity of the mechanical work it may be takes place in an engineering point of view, engineering chemistry point of view like that. So engineering chemistry point of view like that. If some amount of energy will be disappears in one form, that energy will be appears, due to that energy some mechanical work it may be takes place. How much quantity of the energy will be disappears or losing, same quantity of the work done in another one manner. Right? So that's what I mentioned earlier beginning, conversion of the energy to the mechanical work is considered as the heat or energy to the mechanical work, that it may be considered as the thermodynamics also. This first law of thermodynamics, the useful form is the mathematical form. The statements which is not much more useful in CSIR point of view, mathematical form or mathematical equation of the first law of thermodynamics. Mathematical form or mathematical equation is what? For the first law of thermodynamics. Equation is what? So, if Q amount of heat supplied to the system, Q amount of heat supplied to the system, Q amount of heat supplied to the system. By supplying the system Q amount of heat, the internal energy of the system, before it may be suppose system A, internal energy, after supplying the Q amount of heat, this internal energy of the system it may be changed. Changing the internal energy of the system, how much it is going to be changed? Delta E is equal EB minus EA. EB is the final and EA is the initial one. Right? Initial state to the final state, it may be changing takes place. Delta E is the change in internal energy. Internal energy is nothing but this is one form of energy like rotational, transitional, all it may be takes place, that is considered as an internal energy or energy. internal energy, U or E is there, U or E, right? So if it is under constant volume conditions, right, under constant volume conditions, the heat capacity which is considered as also energy or internal energy. Changing internal energy also it may be takes place, which is related with the CV. Later I can explain, no problem. So before that, if it is Q amount of energy, if it is supplied to the system, one, it can be utilized into two forms. One is to change in the Q amount of heat is supplied to the system. It can be used into two types. One is to change the internal energy or to increase the internal energy, to change in internal energy. That means delta E, or sometimes it may be mentioned delta U, change. E is or U is the internal energy, delta E is change in internal energy. After that, while raising that internal energy, again what is happening after that? Some work it may be takes place. Some work done it may be takes place. Work done. Right? So some work it may be the takes place. That means to do some external work. To do some external work. To do some external work, W. To do some external work. That means supplied amount of energy is Q, while changing the internal energy is delta E or delta U, plus work done takes place is W. Work done takes place W. Right? So Q is equal delta E plus W. From this, delta E is equal Q minus W. Delta E is equal Q minus W. Q is equal delta E plus W. Delta E is equal Q minus W. Either delta E or delta U also. Delta U also. This is one form. Right? Next, another one form is also there. Another one form. See, here it is two forms we are using. The first law of thermodynamics. This is one form. Frequently we are using like that in some of the further conversions case. Although another one form is also there. Q is equal delta E minus W, or that means the amount of work it is takes place, W is negative. Amount of work it may be takes place, that will be negative. Here it is positive. Here it is negative. Here it is negative. So that means here it is negative. Here it is positive. If it is negative is there, minus W. Right? So here it is negative and positive values will be, we are using. Right? Negative and positive values will be there. So which one case I mentioned that, I can explain later. So then delta E is equal to what? Q plus W. Delta E is equal Q plus W, or delta E is equal Q minus, delta U is equal Q plus W. This is also one form. So we are using frequently delta E plus W. Here two concepts will be there. Work done by the system on the surroundings. One case will be there. Another one which is work done on the system by the surroundings. Two cases. One is work done by the system on the surroundings. Another one is work done on the system by the surroundings. By the system on the system. Work done. Right? Based on that it may be Q is equal delta E plus W is there, and Q is equal delta E minus W which is there. E plus W and E minus W which is there. In one case. So generally W is equal minus P external pressure into dV. P external pressure into dV. Later in problematic point of view I can explain clearly. So the number of problems also there. Last case, after seeing the concepts, last one we can discuss the problems also. W is equal minus P external pressure into dV. Right? If it is internal pressure is there, that means system pressure, P internal, and surroundings, P external if it is there. internal and surroundings. Internal pressure and external pressure. Before that, the occupying volume, if it is V1, suppose P internal pressure is greater than to the external pressure, P system is greater than to the P surroundings, right? System is greater than to the surroundings. So what will happen? Expansion takes place. Expansion takes place. Expansion takes place. When it is expansion takes place, what will be happen after that? The volume V2 is there. Internal pressure like that. Expansion takes place. When it is expansion takes place, V2 is greater than to the V1. V2 is greater than to the V1. When V2 is greater than to the V1, delta V, P delta V or PdV. P delta V or PdV. dV or delta V is equal to V2 minus V1. This will be what? Positive. When V2 is greater than V1, delta V is positive. When delta V is positive, which value will be there? W value will be negative. W value is negative. Now work done on the system by the surroundings. Work done on the system by the surroundings. Work done on the system by the surroundings is one case. W is negative. W is negative. Next one. If P internal or external pressure is greater than to the P internal pressure. P external pressure is greater than to the internal pressure. So that means suppose P internal is there and P external is there. P internal and P external is there. What is happening? External pressure is greater than to the internal pressure. So this is V1 suppose. If external pressure is greater than to the internal pressure, what will be happen? What will be happen? Compression takes place. Compression takes place. Compression takes place. Expansion and compression. So compression takes place. What will be happen? After that, the volume will be decreasing. Due to that, what will be happen? When V2 is less than to the V1, that means delta V or dV is equal V2 minus V1. V2 is less than to the V1. Then which one is? Delta V is negative. Then W is equal to what? Minus P external into delta V. Already minus is there. Delta V is also minus. Then what will be happen? W is equal positive. W is equal positive. One is during the expansion, W is negative. During the compression, W is positive. Now here it is. Here work done on the system by the surroundings. Work done by the system on the surroundings. Work done on the system. Work done by the system. Work done by the system on the surroundings. Or work done on the system by the surroundings. Work done on the surroundings by the system. Work done on the system by the surroundings. Work done on the system by the surroundings. Work done by the system on the surroundings, or work done on the surroundings by the system. So that's what I mentioned. Two thermodynamic law, first law of thermodynamic forms. Q is called delta E plus W, delta E minus W is there. W value it may be minus and positive it may be there. So whenever it is required, that formulas we are using. Whatever the formula you can use, no problem. If it is plus W can be used. W is equal P delta V we are using further point of view, or PdV we are using. If minus W we are using, in further point of view, W is equal minus P delta V or PdV we are using. W is equal P delta V or PdV we are using. Another one case, minus PdV can be used. So if it is minus PdV can be written, no problem. Delta E plus PdV. If it is plus PdV is written, delta E plus PdV. Further generating the relations we are using. Any one it may be, no problem. So this is the mathematical form of the first law of the thermodynamics. Mathematical form of first law of thermodynamics. In problematic point of view, detailed discussion it may be takes place, right? First law of thermodynamics. But the first law of thermodynamics only which is restricted to the energy case only. Which is restricted to the energy. Which is fixed to the energy. Right? Not explaining the anyone, either temperature, that means heat can flow from which one region to which one region, not explaining the first law of thermodynamics. Heat can flow from which one region to which one region. Next one is second law of thermodynamics. Second law of thermodynamics. What is second law of thermodynamics? Heat can flow from high temperature region to low temperature region spontaneously. Always occurs, heat can flow from high temperature region to low temperature region spontaneously. Or expansion of a gas or pressure, it may be takes place, or expansion of gas or diffusion of a gas takes place from high pressure region to low pressure region spontaneously. Heat, high temperature, low temperature. The diffusion of gas from high pressure region to low pressure region spontaneously. Without the help of heat engine or heat machine, without the help of heat engine or heat machines, heat cannot flow from low temperature to high temperature. Heat cannot flow from low temperature to high temperature. Naturally it is not occurring. But we can use external supports, external heat engines or heat machines, we are using external supports, heat can also flow from low temperature to high temperature. But naturally it is not occurring. So naturally heat can flow from always high temperature to low temperature. That is the second law of thermodynamics. Just simple case. Spontaneously occurring from high temperature to low temperature. Naturally can flow from high temperature to low temperature. Now, in second law of thermodynamics equation, particular equation is not mentioned, but we are using further point of view. The change in entropy delta S is equal Q by T. Change in entropy delta S is equal Q by T. Q is the amount of heat, either it is released or absorbed. Q is equal positive, it may be there, or it may be the negative, it may be there. Q is equal positive absorption of energy. Q is equal negative emission of energy. Heat emitted negative, heat absorption positive. Delta S is equal Q by T. We are using that frequently, second law of thermodynamics form. Exact equation is not mentioned, but we are using. Right? Second law of thermodynamics. Another one law, which is the basic point, zeroth law of thermodynamics. After the first law, after the proposal of the first law and second law, zeroth law will be proposed. Zeroth law of thermodynamics will be proposed. What is the zeroth law of thermodynamics? What mentioned the zeroth law of the thermodynamics? See, listen. According to the zeroth law of the thermodynamics, if suppose A and B systems which is there, A and B two systems, if these two systems will be thermal equilibrium with these two systems will be thermal equilibrium with the third different system, thermal equilibrium with the third different system, suppose A and B systems, thermal equilibrium with the third different system, then automatically those two systems also, that means A and B also thermal equilibrium with each other. A is thermal equilibrium with C, B is thermal equilibrium with C, then automatically A and B is also thermal equilibrium with each other. That is particularly focused on the temperature. Two systems are thermal equilibrium with each other, thermal equilibrium with each other, A, B, which is thermal equilibrium with the C, then automatically those two systems also those two systems also thermal equilibrium with each other. Thermal equilibrium with each other. This is the zeroth law of the thermodynamics, particularly focused on the temperature like that. Thermal equilibrium like the temperature, right? So we are using frequently first law of thermodynamics equation. First law of thermodynamics equation we are using frequently in thermodynamics point of view, right? And in addition to that, some of the basic points also there. Another one or two basic points we are using frequently. And the function enthalpy which is there, I can mention H is an enthalpy. Enthalpy H is equal to what? E plus PV. At constant pressure, the heat content of the system which is considered as the enthalpy. At constant pressure. At constant pressure, the heat content will be equal to the enthalpy. H is equal E plus PV. E plus PV, enthalpy H. At constant pressure, heat content is considered as the enthalpy. And change in enthalpy delta H is equal delta E. P is constant at constant pressure, so that's why P is constant. P into delta V. At constant pressure, change in heat content, suppose change in heat content delta H, suppose, so heat content is H, change in heat content, that means H2 minus H1, H1 is the initial and H2 is the final states. How much it may be, if it is pressure is constant, enthalpy is changed, that means if it is internal energy is changed, E2 minus E1 plus P delta V, V2 minus V1. Then delta H is equal delta E plus P delta V. This type of equations we are using frequently further point of view. If it is an ideal gas system, PV is equal to what? nRT. N is the number of moles, R is the gaseous constant and T is the temperature. R is which one? Gaseous constant. Ideal gas equation is what? PV is equal to nRT. When PV is equal to nRT for n moles of ideal gases, for n moles. If it is 1 mole is also there, PV is equal to RT also there. PV is equal to RT, 1 mole if it is there. Then PV is equal to nRT is there, right? Then P delta V is equal N or delta T or delta N RT also takes place. If it is particularly changed, it may be depends upon the change in number of moles. Delta N RT is also there. Number of moles. If the gaseous equation, delta N is what? N gases of the reactant minus number of moles of gas in the products minus reactants. P minus R. Number of gases of the products minus number of gaseous molecules. That means here it is number of moles of gas in the product and number of moles of gaseous molecules in the reactants. Delta N is equal N gas of the product minus N gas of the reactants. It may be positive or negative, it may be there. If it is in product case, it may be number of moles, it may be more, gaseous molecules is more, than the reactants, delta N is positive. If it is reactants case, if it is more than the product, delta N is negative, that it may be possible. So if it is substitution takes place here in this equation, suppose in another one equation is also delta H is equal delta E plus delta N RT is also there. Delta N RT. This is also one type of equations we are using frequently further point of view. We are using this type of equations. And delta E is what? Delta E is also change in internal energy. E2 minus E1 or sometimes E2 minus E1, or if it is a reaction, it maybe takes place A to B or reactants to the products. So E product minus E reactant, EP minus ER, or E2 minus E1 when it is a system, it maybe takes place like that, it may be there. Change in energy. So if it is reactants to the products, if some energy is releasing, when energy is releasing is considered as the exothermic reaction. Exothermic reaction. Energy is releasing is called as the exothermic reaction. When it is exothermic reaction, energy is releasing. So that means here it is delta E is equal to which one? Negative. Change is negative. That is an exothermic reaction. If it is reactants, where we can supply some amount of energy, then only the reaction will be takes place. Reactants converted to the product by supplying the some amount of energy. This is releasing energy. Excess energy is released. Here we are supplying some amount of energy, then only reaction will be takes place. When supplied energy it may be takes place, that is called as the endothermic reaction. This reaction is called as the endothermic reaction. When endothermic reaction, we have been supplied some amount of energy, so delta E is equal plus and delta is equal minus in exothermic, and endothermic reactions delta is equal plus. Similarly, Q is also plus, some amount of heat or energy will be supplied. Q is negative, exothermic is emitted, absorbed and emitted, right, like that. So next one, basics equation we are using further point of view. Which one? It may be the heat content. So heat capacity, generally is heat capacity. Heat capacity. What is heat capacity? C. Heat capacity. While raising the temp, if it is a substance which is there, the substance temperature is raising to the 1 degree. The substance is there. While raising the temperature of the substance by 1 degree, while increasing the temperature of the substance by 1 degree, how much amount of heat which is required? How much amount of heat or energy is required? That is called as the heat capacity. Heat capacity. Heat capacity is nothing but the how much amount of heat is required while raising the temperature of the substance by 1 degree centigrade. 1 degree centigrade is raising takes place, how much amount it may be required, that is called as the heat capacity. So these are fundamentals, so that's what I can explain fast. We are using whenever it is required. So again, no need to require what is enthalpy and what is heat capacity and what is internal energy and what is ideal gas equation, how it will be obtained. It is not necessary here in this position. So heat capacity. So heat capacity at constant, heat capacity, what is heat capacity? The amount of heat which is required while raising the temperature of 1 degree of substance, that is called as by how much amount it may be heat required to raising the temperature of the substance by 1 degree centigrade is called as heat capacity. Right, that is, suppose if it is substance is there, if it is 25 degree centigrade is there, 25 degree centigrade is there. So to raise the temperature to the 26 degrees centigrade, that means how much? 1 degree temperature if it is raising takes place, how much amount of heat which is required, that is called as the C. That is called as C, that is called as heat capacity. How much amount heat is required, that is called as heat capacity. Right. Next, if it is, suppose here it is how much it may be takes place, 1 degree increasing. Suppose 2 degree increasing takes place, Q is equal to what? C into 2 or 2 into C into 2. If it is 25 degree centigrade to 28 degree centigrade, it may be takes place, then Q is equal 3 into C or C into 3. If it is T1 is the initial temperature, T1 is the initial temperature, T2 is the final temperature, T2 is the final temperature, how much amount of heat which is required to raise the temperature? T2 minus T1. T2 minus T1. When T2 minus T1 means change in temperature, that is delta T. So C into delta T or dt, C into delta T or dt, whatever it may be, you can use small dt or capital delta T. Capital delta is big quantities, D is small quantity, dou is very small quantity, right? Then C is equal to what? Heat capacity. C is equal to what? Q by delta T or dt. Q by delta T or dt. Right? C is equal to Q by delta T or dt is there. Dt is nothing but the T2 minus T1. T2 minus the T1. Right? Now, here in this case, explain another one. Molar heat capacity at constant volume. Another one, it may be the molar heat capacity at constant volume, CV. Molar heat capacity at constant volume is CV. What is that? See, listen. If it is a substance is there, how much heat is required to raise the temperature of 1 degree, that is called as the heat capacity. How much raising the temperature? T2 minus T1, either it may be 1 degree or 2 degree or 3 degree, that is depends upon the T2 minus T1, that is C is equal Q by delta T. Right? So now here it is, this heat capacity C at constant value CV. Constant value CV is what? So molar heat capacity is CV. That means you can take 1 mole of the substance. 1 mole of the substance. The substance, it is 1 mole of the substance. If it is 1 mole of the substance, it may be taken to raise the temperature. 1 mole of the substance to raise the temperature to the 1 degree, how much heat which is required, or the amount of heat which is required to raise the temperature of the substance, to raise the temperature of the 1 mole of the substance, 1 mole of the substance. In the earlier one is just substance. If it is 1 mole of the substance which is taken, molar heat capacity. So now which one condition? At constant value, that means at constant value to raise the temperature by the 1 degree centigrade of the 1 molar substance, how much heat which is required, that is considered as the molar heat capacity at constant value. At constant value, how much heat is required to raise the temperature of 1 mole of substance by 1 degree centigrade is called as the molar heat capacity at constant value. So now here it is, for 1 mole of substance, 1 mole of the substance at constant value, that means CV is equal to what? QV by delta T. CV is equal QV by delta T. Now what is QV here in this case? At constant value, volume if it is constant, while changing the energy, which is nothing but the delta E, So that's what here it is. QV is equal delta E, then CV is equal delta E by delta T. QV is what? Delta E. At constant value, the change in heat which is equal to the change in internal energy. Right? Q is equal delta E, then CV is equal delta E by delta T, or dE by dt in small quantities. dE by dt or delta E by delta T. So then CV is equal, then delta E is equal to what? Delta is equal CV into delta T or d is equal Cv into dt. Cv into dt. If n moles gas, it may be taken d is equal NCV into dt for n moles case. For n moles case, NCV into dt. This is one case. Molar heat capacity at constant value, that means you can take 1 mole of the substance while raising the temperature is 1 degree centigrade. How much amount of heat which is required at constant value? At constant value, the amount of heat which is equal to the change in internal energy delta E. At constant pressure case, amount of heat or change in heat which is equal to the change in enthalpy. At constant pressure, enthalpy; at constant volume, energy. Energy and volume is relation, and enthalpy and pressure is also one type of relation. So Cv is equal dE by dt or delta E by delta T. Right? Next, another one more. In the molar heat capacity at constant pressure. So all these are basic points. So that's what I can explain in short form and very fast. Molar heat capacity at constant pressure, Cp. Similarly, here it is also 1 mole of substance which is taken, 1 mole of the substance. So suppose if it is 25 degree centigrade is there, here it is also 25 degree centigrade. The substance temperature is increasing to the 1 degree, the 1 mole of substance, while increasing the temperature is 1 degree centigrade. How much amount of heat is required? How much amount of heat is required? At which one? Under constant pressures. At constant pressures. So when pressure is constant, the amount of heat which is required while raising the temperature to the 1 degree centigrade by the 1 mole of substance is called as the molar heat capacity at constant pressure. 1 mole of substance at constant pressure, 1 degree centigrade heat is rising temperature. How much amount of heat is required? That is the molar heat capacity at constant pressure. And the heat capacity at constant pressure which is equal to the change in enthalpy. Here it is change in internal energy, Q is equal delta E or du. So this delta E, or sometimes it may be mentioned du also, du by dt. So NCV into delta T or dE or du also, delta E or delta U also, NCV dt. Change in energy is E or U also. Now here in this case, at constant pressure, Qp is equal delta H. Similar like this, Cv is equal Q by delta T. In the Q place what? Qp by delta T. Qp place what you have to substitute? Delta H by delta T or dH by dt in small quantities. Right? Qp by delta T. That Qp is equal delta H. Generally is nothing but Q by delta T. C is equal Q by delta T. What is that? C is equal Q by delta T. At constant value pressure case, Qp by delta T. Qp is what? Nothing but the delta H. Qp is nothing but the delta H. Then delta H by delta T or dH by dt. Then delta H is equal to what? Cv into delta T. Then change in enthalpy which is equal, if it is suppose n moles of ideal gas, if it is there, NCV delta T, or in small quantities dH is equal NCP into delta T. This is the Cp at constant pressure. So that's what I mentioned, Cp. Cp is equal delta H by delta T. Cp is equal delta H by delta T and Cv is equal delta E by delta T. You must remember that. The two equations. The equations are important here in this case because in the basics point of view directly questions are not there, but equations we are using in the further point of view. These equations are we are using in further while changing the mainly focused on the entropy and free energies, gives free energy, and Helmholtz free energy and chemical potential, like the terms will be there. And changes on that in different systems, while temperature pressure is changes, temperature value is changes, temperature and some other concepts based on that. So further thermodynamics is there. Now another one, Cp minus Cv is equal, Cp minus Cv is equal, Cp is what? dH or delta H by delta T. Cv is what? Delta E by delta T. I mentioned that. Based on that, delta T, if it is common, what will be happen? Delta H minus delta E. I already mentioned that earlier one. Delta H is equal to what? Delta E plus P delta V. Already I mentioned that earlier one. Based on that, delta H is equal to E plus PV. At constant pressure, the change in heat content is nothing but the delta H. I already mentioned that earlier one. Then what is that? Delta H is equal to delta E plus P delta V. So then in the place of delta H, we can substitute P delta V minus delta E by delta T. Then this is cancellation takes place. Which one is there? P delta V by delta T. Now, if it is n moles of an ideal gas which is there, PV is equal to RT, suppose PV is equal to RT for 1 mole of ideal gas, then P delta V is equal to what? R is a constant, gas is constant for 1 mole of ideal gas. For 1 mole, P delta V is equal to R delta T. So then in the place of P dV, R delta T, if it is substituted by the delta T is there, then what is that? Cp minus Cv. Then which one is there? Cp minus Cv is equal to is what? R. Heat capacity at constant pressure minus heat capacity at constant volume, which is equal to the gaseous constant. Then Cp is equal to what? Cv plus R. Cp is equal Cv plus R. That one is also there. For monoatomic gases, some values are there, Cp and Cv. For diatomic gases, some value is there. For triatomic gases, some values are there based on the rotational degrees of freedom and transitional degrees of freedom. So again, it may be whenever it is required, I can explain on that manner. So Cp is equal Cv plus R, like this is also fundamental equations which are there. Fundamentals, Cp minus Cv, like this. Right? And also another one I mentioned that today's topic, before that going to be further point of view. Another one more fundamental. If it is, the terms are there, we are using further point of view. The terms isothermal and adiabatic and isochoric, we are using further point of view. Isobaric. Isothermal, adiabatic, isochoric, isobaric. What is that meaning? Isothermal process. What is that? Isobaric process. Isobaric process is what? Isochoric process is what? Adiabatic process is what? We are using further point of. When isothermal process means the temperature of the system is constant. When the temperature of the system is constant. When a system is maintained at constant temperature. The system is maintained at constant temperature is called as which one? Isothermal. When constant temperature means the change in temperature T2 minus T1, which is equal 0. Temperature is constant, that means T1 is equal to is what? T2. When T1 is equal to T2, T2 minus T1 is equal 0. Delta T is equal 0. T is constant, change in temperature is 0. Not delta T value is not constant. T is constant, change in temperature is 0. It may be same. Next. In adiabatic process, change in heat. So that means heat will be constant. While temperature is exchanging from one region to another region to maintain the constant. So, but here it is, change in heat will be constant. Heat cannot exchange with the surroundings like that. Here it is, temperature is constant. Here it is, heat is constant. Adiabatic. Next, isochoric. Isochoric case, what will be happen? The system is maintained at constant volume conditions. Constant volume conditions. That system is called as the isochoric. Well, volume is constant. That means volume is constant. Change in volume delta V is equal to 0. Delta V is equal to 0 means V2 is equal to V1. Or V1 is equal to V2. Then delta V is equal to V2 minus V1. Both will be same. That value will be 0. When isochoric process case, which one is there? V is constant, delta V is 0. And isobaric process is what? When pressure is constant. That means system is maintained at constant pressure conditions. System is maintained at constant pressure conditions. That system is called as the isobaric system. When it is isobaric system case, pressure is constant. Change in pressure is 0. dP or delta P is 0. That means P2 is equal to P1, constant pressure is maintained. Isothermal, isochoric, isobaric and adiabatic process. Right?